So when we think uniform fields, uniform electric fields, we think parallel plates. So that's the topic that we're going to be dealing with. So here it says compare the electric field around a point charge and the electric field between two parallel plates. So far what we've been doing is, say we just have one charge and it's making an electric field. What is the direction of this electric field?
Outwards.
Outwards. So we would draw in. Now, if I was out here, that's a weak electric field. And if I was, say, really close, that would be a strong electric field. Just like how you do in your poster, where you have to label in your poster a strong versus weak one. But the question that I asked you today was, how could we make it so that it was the same, that a charged particle or a point could experience the same thing? Well, we think about, just like we have our two benches, these are our two benches. So here, this is Hannah and I, we're the positives on the benches, and then Jessica and Matt were on the other bench, and they were negative. So it made a parallel plate that had the electric field going in this direction. So let's think about this for a moment. When we found out the electric field strength at different points here, we would use the formula E equals KQ over R squared. But here, it doesn't matter what point we are at. At every point, it's the same. Same. It'd be the same electric field everywhere that it goes. Okay? Around the corners, it's a little bit off, but we assume that for the questions that it's talking about inside. How do we make this electric field? Well, you have a battery. Now, to show a battery, we use different symbols to show a battery. So this whole thing, we say this is a battery. Battery. Now, where the line is small is the negative end. So this end is negative. And this end is positive. So there will be a negative and positive end to every battery. So because this is the negative end, that means the electrons are going to flow that way, that direction, and that's why this plate is negative. So if in questions it asks you to figure out which plate is negative and which is positive, you can look at the battery often. Or some of the questions might ask you to draw in the battery. So just know where it's negative is where the electrons flow into. Okay, so as I was saying, we would use this equation for this type of scenario. But since the electric field is the same regardless of the R, or the distance, we can never use E equals KQ over R squared for parallel plates. You can't do it. It's not allowed. Because it doesn't make physical sense, because this law doesn't apply to this situation anymore. Okay, so only this equation for points, not parallel plates. Yes? Okay. So parallel plates are an example where the electric field strength is uniform. So when you hear the word uniform, you think parallel plates, or uniform means the same, right? So the electric field strength remains the same. So because we can't use this formula, we need a different formula. So there's different principles that we need to think about with electric fields in order to know what formula to use. So electric potential energy, so we're going to think about potential energy right now, is very similar to gravitational potential energy. So we're going to kind of take that knowledge from Science 10 essentially and apply it here. So a charged object inside a uniform field can have a high electric potential energy and a low electric potential energy. The law of conservation applies, and electric potential energy can be converted into kinetic and vice versa. So in our example, where we had the charged particle that was in the middle, you said that it would accelerate toward the negative, right? So it will change in its energy. If it's going closer to you guys, it will have a lower potential energy, but a higher kinetic because it's accelerating. So how do we represent that? Well, say we have again our plates, like here, here's our positive, here's our negative. Like in our example that we talked about, say we have a positively charged object or particle here. What's it want to do? It's going to want to move this way. It's going to have a force exerted on it to go down toward the negative plate. So we can talk about its energy then. So at this point, it has a high potential energy because it has the potential to move. It's going to want to be attracted to the other plate. So if something has a high EP, conversely it has a low EK. And then once it reaches the negative plate, or just like potentially right before, it will have a very low EP and a high EK. Kind of like our pendulum examples that we did in Physics 20. Therefore, uniform electric fields or parallel plates are a method to accelerate or decelerate charged particles. So when we think about this, we need to think about acceleration principles. Now, an application of this is something called gel electrophoresis. Have I ever told you about gel electrophoresis? And actually, I brought this up last year, and it was on the diploma, so I thought it was good to maybe tell you about it. So let's just wiki this thing. So gel electrophoresis is a method for separating and analyzing macromolecules. So most often it's used in DNA. So what you do is there's this gel kind of medium, and they put the DNA in, and DNA is electrically charged. And so it will want to migrate, so they set up a parallel plate, so it will want to migrate from one side of the plate to the other. How much it migrates depends on how big it is. So then it takes DNA and it breaks it down into smaller fragments. So then one person's DNA, gel electrophoresis, is very unique. Nobody else's looks the same. Okay? So it would look like that. That's like what you see after, and then you fluoresce it. So that's the fluoresis part of it. And you can look at the different DNA bands. So see here it shows this is like the negative end, and here's the positive end. So it sets up a parallel plate. And the DNA wants to migrate to the positive end. But some of them don't get all the way because they might be too heavy. They might be too big. See, these ones are really thick. They don't move as far. So that's the kind of just general idea. So if you're being asked about gel electrophoresis in say, a test, you won't have to analyze the gel, like the actual data. You'll just be told like that it's set up and you have to apply your knowledge of parallel plates to this idea. So it's just good to know kind of an application point so that if it's sprung on you in a diploma, it's like you have a little bit of context, right? So, and I did see it on the last diploma, so it's, I've done it before in university. Mine was awful though. So it takes a little bit of skill to get good at it. It's a lab skill. Anyways, okay, so let's move on.